All right, let's do this first virtual modern physics lesson. Hopefully you guys are doing all right. Sit down on the couch and watch this. It'll feel like you're in the classroom, falling asleep. Hopefully not. Stay awake. Wake up. So we get to actually talk about some physics again. Thanks for going on that climate change detour. I just really wanted to practice looking at data, whether you're an activist or a skeptic. Just look at data and that can inform what you think about. So I'll look at your papers. Hopefully they got turned in and everything's cool there. Thanks for researching those. I'm legit interested. You guys, you guys may have looked at a correlation that no one's ever looked at before, which is cool. So there's tons of data out there, but maybe no one's ever looked at how this variable correlates with some other variable. So some cutting edge physics there. Well done. And speaking of cutting edge physics, we get to talk about quantum field theory. And this is effectively the most bleeding edge of physics that we have right now. So quantum field theory is the most up-to-date theory in all of physics. There are theories beyond this, like string theory, but, like string theory. But, I mean, we don't really know if string theory is true or not. So these are like speculative. There's lots of speculations beyond quantum field theory, but as of now, quantum field theory is basically the most cutting edge physics that we're pretty sure about. And I guess I should rephrase this. I'll rephrase this in a Popperian way. Because some people are sure about string theory. Okay, so here's what I mean. Quantum field theory is the most up-to-date physics theory that we have an abundance of evidence for in the sense of it predicted, it being quantum field theory, predicted a bunch of results, and with particle colliders, we confirmed those results over and over and over and over. So this is one of the most well-confirmed theories there is out there. We're pretty sure it's not the final word. For one, it doesn't include gravity at all. So if your theory got no gravity, it's probably not 100% correct. So there's no gravity in quantum field theory. Also, there's reasons we'll talk about later to think that quantum field theory isn't the final word on anything, even for like electric or magnetic theories. Probably not the final word, and we'll talk about why, but it is the most up-to-date theory that we have that has been abundantly verified through experiments. So string theory got no experimental verification yet. So even though some people think it's true and it's more cutting edge than quantum field theory, it hasn't been verified yet. Quantum field theory, bleeding edge of physics. But, physics runs slow. This thing's been around for 40, 50 years. So what is quantum field theory? Well, we've talked about quantum mechanics, wave functions, Niels Bohr, measurement problem, all of that business. We talked about special relativity with time dilation and different observers using different coordinate systems, not agreeing on this, that, or the other. I mean, the obvious question is, okay, if quantum mechanics is the rule set you use for things that are really small, so if you're talking about atoms, electrons, if I have to use quantum mechanics to describe those things, fine. And if special relativity is the rule set that I have to use to describe things moving really fast, so if you start moving near the speed of light, the regular physics, classical physics isn't going to work as well. There are going to be deviations from the predictions. So if you have to use special relativity for things that are moving really fast, what happens if you have something that's really small, like an electron, moving really fast, like near the speed of light? Well, then you need a special relativistic theory of quantum mechanics. So in the quantum mechanics we had the Schrödinger equation. There was no time dilation in here. When we were talking about time, we weren't like, oh, with respect to observer A or B. It was like, no, we just assumed there was a clock, a universal clock, and everyone agreed on it, but that's not right. We know in special relativity, observers start moving really fast relative to each other. You're going to have to specify time measured with respect to whose clock. And so you need to incorporate all these rules over here, these Lorentz transformations, the fact that E is gamma mc squared, not just like 1/2 mv squared, time dilation and all that. That all has to get incorporated over here somehow. So how do you do that? Well, I mean, one thing is we have new rules for energy, right? Energy isn't just 1/2 mv squared anymore. When in class, we derived the Schrödinger equation. we kind of motivated it. We motivated the form of this Schrodinger equation by using ideas like kinetic energy is 1/2 mv squared, or momentum is mv. Classical ideas of physics. That's how we derived the Schrodinger equation. But, those aren't actually completely true. If you go really fast, you need to use these better formulas for energy or momentum, promentum, if you like. Credit to Camden there. Well done. Promentum. If you use those formulas, you're going to get a different equation. It's not the Schrodinger equation. It's going to be analogous to the Schrodinger equation for quantum field theory. So that's one difference, but that's not that big of a deal. It's like, okay, this formula is going to look a little different. The big deal is this. E equals gamma mc squared. What that means is if you've got enough energy, you can create matter. So if I send in a bunch of photons with a ton of energy, maybe I had no electrons to start with, but if I just ram a bunch of photons into a collider here, if I send them in with enough energy, even though there were no electrons before, I could create electrons out of nowhere, which is completely new. This is something completely new to quantum field theory that wasn't in special relativity or quantum mechanics at all. So this is a completely new aspect. And so what I'm saying is this. The questions we asked the Schrodinger equation to figure out were questions like, hey, if I send an electron through a double slit, what are the odds of finding it over here? Maybe it's like 40%. What are the odds of finding it over here? Maybe like 10%. What are the odds of finding the electron in here? Maybe 0%. But I wasn't allowed to ask the Schrodinger equation, if I send in one electron through a double slit, what are the odds of finding 2 electrons over here? It's like, no, that just didn't happen. You send in 1 electron, you get 1 electron. What are the odds of sending in an electron and finding no electrons? It's like, no. The electron shows up somewhere. But in quantum field theory, this can happen. So if you send in a bunch of particles together with enough energy, you can just start creating particles seemingly out of nowhere or destroying them, right? So these photons may disappear. You may get electrons coming out. So particles can get created and destroyed, and this was not something that our previous Schrodinger equation and interpretations could allow. So I could ask, what are the odds of finding an electron in a given spot? I wasn't really allowed to ask, what are the odds of destroying the electron? That had odds of 0 according to the Schrodinger equation. But in quantum field theory, you're going to have to figure out what are the odds of this particle getting created, what are the odds of this particle getting destroyed. So there are far more options available in quantum field theory, which is kind of cool. So let me get rid of this. Quantum field theory is really a special relativistic theory of quantum particles, which is like really small particles. So atoms and quarks and all that nonsense. Particles can get created and destroyed. That's probably the defining feature of quantum field theory. And this could not happen in old quantum mechanics. So what you'll see, we don't draw force diagrams for quantum field theory, but physicists love diagrams. Like no matter if they're drawing force diagrams or if they're doing quantum field theory, they're going to be drawing something. So we draw these Feynman diagrams, and these are ways to keep track of, okay, what could turn into what? So in this scenario here, you've got like a photon or some sort of Z particle coming in, and it turns into an electron and an anti-electron. So there's these creation events that can occur. And trying to keep track of all the different ways these can happen is a big part of quantum field theory. So what are the odds of, in other words, a big part of quantum field theory is what's the probability of some group of particles turning into some other group of particles after you smash them into each other. This is sort of the main thing that quantum field theory is concerned with, and it's one of the main things particle physicists are concerned with. Is if, okay, let's say we build a particle collider and I slam a proton into another proton with a given amount of energy. What we want to figure out is like, what are the odds of, electrons coming out? What are the odds of a Higgs particle coming out? What are the odds of photons coming out? And each one of these has a distinct probability. And again, it's probabilities. You can't say for sure. I cannot tell you if I send in protons with exactly this energy and exactly this angle, I will get exactly 1 Higgs out or something like that. All I can tell you is the probability it's going to occur. So quantum field theory is still a probabilistic theory. All of the riddles of the quantum theories we had before like, hey, do these things have exact properties before you measured them? That all comes over wholesale. Like, that's still all included in here. We don't solve that problem. Quantum field theory doesn't solve the measurement problem. It doesn't really solve the like two-slit, double-slit problem. Like, all of these mysteries are still incorporated in quantum field theory. It's just that in addition to all that stuff, you get to create these particles and destroy them. And that's why we build particle colliders. So it's like, you want to test quantum field theory, you better send in a lot of energy. So we build a particle collider where you can send in particles at each other with a lot of energy, and then you get a bunch of particles out. You build a detector around it, and then you can see if the predictions of quantum field theory are true or not. That's what we've been doing. So who cares about quantum field theory? Well, I do. So this is why I went to graduate school. I wanted to know. It's like, I was like, damn, dude, I want to know how this works. How does this stuff work? How does quantum field theory actually work? Just as a, just wanted to peel back the layers of reality to peek underneath. Just, I'm a nerd. Who else cares about it? Well, like, Hawking, he was trying to figure out how quantum field theory might mix with gravity. That's how he got famous. This guy here is Richard Feynman, one of the most famous physicists in the 20th century. He was largely credited, him and other people, credited with figuring out how QFT is going to work. He figured out specifically the quantum field theory for, electric fields, called QED, which is just a specific version of QFT. And this is Freeman Dyson. Hopefully you guys remember Dyson. This was the guy who also helped create QFT. He did not get the Nobel Prize, but he's widely regarded as one of the founding fathers of quantum field theory. Bad news, Dyson recently died, like in the time where we were talking about climate change, because this guy's also one of the most famous skeptics, or he was. Dyson died recently, so like in the last couple weeks, I think Freeman Dyson died, so the world lost a freaking genius here. Freeman Dyson came up with all kinds of stuff. So, condolences to him and his family. Hopefully they're doing okay. Practical applications? Well, not a whole lot. So has QFT actually led to the building of anything cool? Not really, not yet, but this is how it usually works. There's like a lag of like 30 years between fundamental physics and engineers developing some sort of new tool or application that we can use. So nothing much yet. I mean, the World Wide Web, physicists take credit for the World Wide Web because that's how they were initially communicating their data on these particle colliders, but it's not like if quantum field theory isn't true, it's not like the World Wide Web is based on quantum field theory. It's just in doing the experiment to try to confirm or disconfirm quantum field theory, we needed a way to communicate the results, and physicists came up with the World Wide Web. And so, does that count? Not really, dude, but maybe one day we'll figure out a way to use quantum field theory to build a better, energy source, battery. Who knows? It's hard to say how these things turn out. Okay. And so how do you do it? You build, this is the LHC, particle collider. Look at this thing. This is how we measure and test. I should say test here. That's how we test quantum field theory. Popper wouldn't care. Karl Popper would not care about your theory. You wouldn't even consider it science unless you could test it. Can you disprove it? Yes, we can. So you slam particles into each other. So this is the injection ring. This thing is enormous. So let me just give you a sense of scale. So if you can see this scaffolding, this is a scaffold people stand on. The person would be like, this is like how big a person is. Like that big. This is how big the collider is. This thing's freaking enormous. You send in these protons after flying them around at ridiculous speeds and near the speed of light. They're going to come in here. There's another beam that comes in from the other way. And they collide and all hell breaks loose. This is the detector. So, the collider is, so first thing you need to do is get these protons up to speed because they need to have a lot of energy. You want to make a lot of particles, and those particles might have a lot of mass. Well, E equals gamma mc squared, so you better put in a bunch of energy into there. So this here, and then the other part is the detector. So this entire apparatus here is the detector. This whole thing is just here to detect all the crap that flies out of here. It's enormous because it's layer upon layer upon layer upon layer. Because as these particles fly out of here, you want to detect them all, and the way you detect them is going to be different depending on which type of particle they are, and you don't want any to escape. If any of these particles get out of here without you noticing, well, crap, now it's like, shoot, did we discover some new property? Is energy not conserved or something? It's like, well, no, you probably just lost some energy to stuff that you didn't find. So you want to make sure you build a detector that captures as much as you can so that there's no weird mysteries going on like that. And this thing's expensive, 4.75 billion. I believe it's the most expensive experiment mankind's ever done. So a bunch of countries have pitched in, and this collider is ridiculous. You've got all these different detectors. So you've got your Hadron calorimeter in here. This is to detect any protons and extra neutrons and crap that fly out here. Crystal electromagnetic calorimeter. This is to detect anything that's charged. So if you can find it two ways, better than one way. You've got the muon chambers out here. Muons make it a long way before they get detected usually. You've got the muon chambers on the outside. Again, just layer upon layer upon layer. You get a scale of how big a person is right here compared to this thing. It's just monstrous. And all of these are sending all this data to computers, but the amount of data is just absurd. So what you have to do, your computer can't store all this. So you're running this experiment. All hell's breaking loose. You're just constantly doing it. It's not like you do it one time. It's a probabilistic theory. You got to run this tens, 20s, millions, trillions of times in order to gather enough data to be sure about your probability distribution. So you're always running this data, and then you check. And most of these events are just boring. It's like, got another electron. Woo, whoopee, we discovered another electron. But some of these events are like a Higgs creation. So if a Higgs particle flies out, that is an interesting event. That's why they built the LHC in large measure, to try to tell if there's actually Higgs particles or not. We thought there was, so this was a way to test it. So they really wanted to make sure this detector was going to be good at detecting any Higgs particles that fly out. So those are events that you're interested in. So you're constantly just filtering out. There's a process where you just filter out, no, it's stupid event, we don't care about that. Oh, this one looks interesting, and then it goes through this filtering process, and finally it may store that data as something that might be interesting. So this is how we measure it. You're creating all these particles in here. Costs a lot of money. It's enormous. I don't know if you've ever seen the scale of the LHC collider. It is ginormous. This is France in here. This yellow line is the border between France and Switzerland. So this is the size of the racetrack we're racing these protons around. So you can see each little field in here. These are like farm fields, you know what I mean? And so these are like football field sizes or bigger. And so that's the scale of the tube. It's all underground. So this is the tunnel through which these protons get accelerated at near the speed of light, very near the speed of light. And then you smash them at, so I think we just looked at CMS. So that detector I just showed you, I believe is over here, just be a little dot. So the underneath, there's a spot where you're going to collide them here. There's other places you can collide them. So different detectors might be looking for different things. So Alice is a different detector located over here. Atlas is a different detector, and so on. But this is the tunnel where you run them. You run them other, opposite ways. So protons coming that way, protons coming this way, and then you just fine tune them and smash them over and over and over and over, and look at all the stuff that comes out. And then you could tell, okay, quantum field theory says this process should happen. You should create Higgs at 20% rate with this collision. Then you could just check, keep running this over and over and check. And they did, and it worked. And they predicted the Higgs should come out with certain probabilities, and they verified it. And so we're pretty confident that quantum field theory gives you an accurate description of how these particle creation processes occur. Okay, so how do you quantum field theory? Well, okay, so you draw a Feynman diagram. So what you do is you figure out, okay, what particles are coming in, and then you ask, what are the odds of certain particles coming out? That's really the name of the game. So if I send in 2 protons at this energy, what are the odds of this collection of particles coming out? And there's an infinite possible amount of end results. So most people use Feynman diagrams. I showed you who Feynman was a minute ago. Let me change the color here. So a Feynman diagram is a way to keep track of all the ways these particles can interact, get created, get destroyed. They're a graphical way to represent it, which is nice. And so they'll let you keep track. We're going to use these a ton. This is how we going to do quantum field theory. So we're going to figure out the possible Feynman diagrams. They're useful in giving you an intuition. It's hard to get intuition in quantum mechanics and quantum field theory, but Feynman diagrams give you a little bit of intuition about what's possible, what's not possible in quantum field theory, or what's likely, what's not likely, what's happening under the hood. So we can kick the tires using Feynman diagrams. They're also a way to represent complicated mathematical calculations. We are not going to do the complicated mathematical calculations. For one, it's all calculus based. For two, I mean, if you thought quantum mechanics was complicated, quantum field theory is absurd. So I'll show you. This was in graduate school. I had to take quantum field theory. I took like 3. There was like quantum field theory 1, 2, 3, and then there's other courses that are basically quantum field theory. They're just named other things. So this was one of the calculations I had to do. This is, let's see, I think time's running vertical here. I think this is electron turning into photons, or it could be electron scattering. I forget which way. Different people run time different ways. But anyways, this is either an electron interacting with a photon, or it's an electron, annihilating with a positron and turning into photons. And so this is what the calculation looks like just for this one diagram, right? This is one of the simplest Feynman diagrams you could ever have. There aren't that many particles involved. Pretty simple. Okay, this is the calculation to figure out the odds. Oh yeah, sorry, I wrote it right here. I'm a freaking moron. Right here, this is electron-positron annihilation. So what we have going on here is a positron and an electron combine. We're trying to figure out the odds of them turning into 2 photons. And this is just one of the parts of the calculation for this thing. So it's one little calculation for this thing. How do you do it? Oh, okay, so let me get out of here. You're going to have to do this math, do all this math, do all this is just for that calculation. Do all this math, do all this math, do all this math. You keep going. You're trying to figure out the odds. So don't complain about your homework to me. This was one problem. Every page here is one problem for quantum field theory. So this was my homework in graduate school. You keep going. You find the trace of all of that. Like even every one of these things is standing for a bunch of stuff. So not only are there a bunch of terms, each one of these terms is usually standing for 4 terms themselves. You keep going. You keep going, you keep going, you keep going, you keep going, you keep working. I remember sitting in my apartment just doing this for hours and hours and hours, and almost finally get there. Whew. Figured it out. Got to the answer. This is the way to figure out. It's called the scattering cross-section. It's sort of telling you like the odds of finding a certain event if you measure it in every direction. So you finally get to here. This is the answer. After 9 pages, that's how much math it takes to do one little quantum field theory calculation for this little diagram. So we're going to draw the diagrams. We are not going to do the math. If you want to do the math, major in physics and then go to grad school and then you can do the math. Honestly though, like I get far more intuition just teaching you all how to do Feynman diagrams because there's far more intuition to be had here than there is in the math. You get to the end of the math and you forget what you're even doing in the first place. You've been cranking away at this, grinding at this thing for hours. So we're going to gain intuition by looking at Feynman diagrams. We are not going to go through the math to figure it out. It's not really necessary, and this is high school after all. What are we doing over here? Okay. So that's what we're going to do. I'm going to show you how to do some of these Feynman diagrams. Let's go. How does this work? So let me show you how to do a few, and then I'll have you try a few here. So Feynman diagrams for QED. Okay, so there's a quantum field theory for each force, each fundamental force. The easiest one by far is just the electric force. So if we want to describe the electric force, quantum field theory, it's called QED, quantum electrodynamics. This is just the quantum field theory of the electric force. You can also have a quantum field theory of the weak force. You can have a quantum field theory of the strong nuclear force, and so on. So QED is easy. This is the one Feynman came up with. It's the easiest one. Well, it's not easy, but it's the easiest one of the quantum field theories. And it's easy because there's only one possible interaction vertex. We call these vertices right here. Except there's only one here. So I don't even know why I'm writing vertex here. So there's only one vertex. In other theories, you're going to have a bunch of these possible interaction vertices. This one's electron, electron, photon. That's it. And I mean, it's more complicated than that because it could be positron, electron, photon. It could be positron, positron, photon, or it could be electron, electron, photon. But it's really just like, electron and positron are kind of two sides of the same coin. So the only interaction vertex you get is electron, a positron, or an electron, electron, or a positron, positron, and then one photon coming out. You are not allowed to have like electron, positron, and two photons coming out of this dot. You're not allowed to have like two positrons and an electron come out. No, there's got to be one photon and then two electron-like things. You might think this one's okay, but it's not. So you got to run these arrows. They have to continue on. Notice this arrow continues on. Notice this arrow continues on. It never runs into the other thing. This is like a transmutation. You're not allowed to have these arrows run into each other. I'll tell you why. Because time's running this way. So what we have up here is an electron that just scatters off of, emits a photon and then scatters this way. So you had an electron come in, the electron goes out, but it got scattered by a photon. It's like, fine, okay, cool. What happened here? You had a positron that got scattered by a photon. What happened here? You had an electron and a positron come in. Remember, I think I've told you this. We draw the arrow on these positrons backward. You might be like, wait, but the electron, time's running this way. Why are we drawing the arrow of the positron as if it's going back in time? And the reason is these positrons are indistinguishable from electrons going back in time. So I find it helpful to just think of these positrons as electrons that are going back in time. So for this event here, what happened was the electron came in, got hit by a photon so hard, it got knocked backwards in time. And again, what that means is if we're watching this, we're riding on time this way. At any given moment, we'd be like, wow, look, there's two particles here. There's an electron and there's a positron. We'd be like, oh my God, they're getting closer together. And then, oh my gosh, they disappeared. We'd be like, holy moly, the electron, positron disappeared over here. But, from a God's eye perspective, God be looking down like, nah, man, that electron just got bumped back in time. You kept drifting forward in time. You thought there were two things. There was only one thing. It got knocked back in time. Again, whether that's the correct way to interpret this, there's no way to tell. There's no way to tell the difference between a positron going forward in time and an electron going back in time. But for me, it clears up a whole bunch if you just think about positrons as if they're going back in time. And it's freaking awesome. Okay, so this is the only type of interaction you can get. The arrow's got to keep running. That is to say, the electron maintains its identity as an electron. The positron maintains its identity as a positron. Or if you've got an electron and then afterward you have no electron, you had to bump that thing back in time and it became a positron. You're not allowed to have like electron turn into positron as we go forward in time. This is weird. Like this can't happen. If you end up with a positron, it's because there had to be an electron here that bumped it back in time, but that means this had to show up before the event happened. So you should have another line this way. That's why the line has to continue on. So those arrows can't meet, in other words. So what does this mean? Okay, so the types of problems we're going to try is this. So I gave you this. So feel free to bust this thing out. Break out your packet. Grab a pencil. Pencil will probably be good. Draw light. You might want to draw on a separate sheet of paper because there's going to be a lot of possible ways to combine these together. So with this first Feynman diagram, we can ask, what are all the ways that an electron and a positron could come together and create two photons? Now you might be like, 2 photons? That ain't possible. Electron and positron come together, they can only create 1 photon. So the odds are 0 here, right? No, because you can combine a bunch of these together. These are like little Lego bricks. You can combine these together to form more complicated processes. So using only these, which is really just one, using this one vertex, how do I connect these incoming states to the outgoing states? So this is kind of cool. It's like a puzzle. So what could you do? I'll show you a couple. I want you to find a third way to do it. There's literally infinitely many ways to do this. And when I say literally infinite, I mean literally infinite. I don't mean really big. I mean this goes on forever. There are an infinite number of ways to connect these incoming states and outgoing states. So let's do one. Let me show you how this works. So you could have this electron and positron come together, and you could do like that. And I check my arrows. Yep, my arrow continues on. They don't like run into each other or anything weird like that. So it's not like the arrow's coming in this way or something like that. And then what's got to come out of there? I'm only left with one option. It's got to be a photon. I'll try to color code this. Photon comes out, and then I'm like, oh crap. But I need 2 photons to come out. It's like, well, okay, so here's what I'm going to do. Check this out. One way to do this is I'm going to send out a electron here, positron here. So electron, positron. And this is an allowed vertex. Sorry, this is an allowed vertex. This is a photon, electron, positron. That's perfectly fine, and these arrows don't run into each other or anything. And then up here, look at, I've got an electron, I've got a photon, the other leg, you get 3 legs on this thing, electron, photon. The other one has to be either electron or positron. So I'm going to run down this way and watch what happens. Boom. It's like, whoa, you get this triangle. So you check each vertex, right? So does this vertex, we'll check over here. Is this one allowed? Electron, arrow continues, and then you get a photon out. Yep. So photon, electron, arrow continues. And then photon, electron, arrow continues, photon, electron, arrow continues. And you're like, what the hell? What is this little like triangle of electron here? We call these virtual particles. You don't ever see these. It's like, what is going on here? These are all virtual particles. Now, virtual means like they aren't part of the incoming system. They weren't what we sent into the collider. And they aren't what come out of the collider. We never detect these. But all of this mess in here are virtual particles. They're particles that sort of popped into existence, and they pop out of existence, and then we get other particles at the end. Now, you can ask, like, do these really exist? You could claim these are just mathematical, like, representations of how to get odds. I don't know. Physics community is like most things in quantum mechanics, we're conflicted on this question of like interpretation. Do these actually exist? Physicists talk about them like they actually exist, but we talk about lots of stuff like it actually exists. I'm under the persuasion that these are more like mathematical tools, but that doesn't say a whole lot because I'm under the impression that everything we say, all of language is just the tool that we shouldn't consider as somehow ontologically existent in some way beyond that. So do they exist? Maybe as much as anything else exists. Do those things exist? I don't know. Look, I don't want to get too deep in there. I don't even know if that question makes sense. But these virtual particles, we're going to talk about them as if they get created and then they lead to other things. So whether they exist or not, speaking about them as if they exist definitely gives us a way to make correct predictions. So if that counts as exist, then sure. So we get 2 photons out here. So this is one way to make this happen. This is one way you send electron, positron in, they annihilate, and you get 2 photons out. So this is a way that this can happen. What's another way? This one's actually kind of complicated. Notice, here's what you should do when you do this. You should count the number of vertices. So we had, let me see, I'm able to draw squares with this thing here. We had 1, 2, 3, 4 vertices. And that's important because the more vertices you have, the less likely this is going to, I shouldn't say it that way. The more vertices you have, the less this particular drawing will contribute to finding the overall probability of what's happening here. So this one had 4 vertices, That's not going to be as important as one, if I could find a 2 vertice option to connect these incoming and outgoing states. That 2 vertice option would much more contribute to the overall probability of what's happening here. Because remember, I said there's infinitely many of these. So if you heard that and you wondered, well, then how do we ever make a prediction? You can't calculate an infinite amount of these. It's like, yeah, no, you can't. You cannot. So what we rely on is that these get more and more complicated. The 100th possibility is going to have a ton of these vertices in here. Because I could keep doing this. Remember, I could keep I could keep throwing things in here. I could have a weird loop of electron or something where photon comes in, turns into this. You get more of it. I can keep adding these if I want, but I keep adding more vertices. And it turns out the coupling constant for each one of these vertices, you get for electric forces, you get a 1 over 137 is just like the number, the sort of electric constant that goes along with QED. And this gets factored into your little calculations here. So every vertex you have, remember that crazy calculation I showed you with the 9 pages? If you go through and do the calculation, every one of these vertices adds up to this. So you get a 137 times another 137, 1 over 137, times another 1 over 137. So the amount that this little drawing contributes is going to be proportional to the number of vertices it has in terms of this. So think about it like this: 1 over 137 raised to the n, where n is the number of vertices, and then that all gets multiplied by your crazy calculation. So that crazy calculation for the 100th term doesn't even matter. Look, 1 over 137 to the 100 is basically 0. I mean, it's out in the way out in the decimals that we're not going to be able to measure precisely enough to care about. So that's the way we do quantum field theory, is we figure out the most important terms here. And most important means the least amount of vertices, because those are the ones that factor into predicting the overall probability of these incoming leading to those outgoing. Notice, for all these drawings I have, they're all electron, positron turning into 2 photons. But the innards here, the guts, what virtual particles I draw, that will vary how many vertices I have. And if I draw some crazy combination with 1,000,000 vertices in here, it basically doesn't matter, because that contribution to the probability is just canceled by the fact that it's 1 over 137 to the 100 or whatever. So the way you do this calculation, the way you would do it, is you'd figure out all the possible ways. If you wanted to get the exact answer, you'd figure out all the possible ways to connect this incoming and outgoing state, and you'd add up all those probabilities. It's what is the total probability of electron, positron turning into 2 photons? Theoretically, you'd have to add every one, which is infinite. But again, these ones that further on, they don't really matter because of this fact here. So we're going to only draw maybe the first, 3, 4, 5 or something here. And the ones after that don't really matter. So that was one option. To give you an idea of what else is possible, let me get rid of that. Here's another possibility. I'm going to just check this out. I'm just going to run this electron down this way. This is not what I did before. What I did before is I had these connect and then 1 photon came out. But look at what happens now. Now that I just run this all the way through, which is allowed, it's allowed if I have photons coming off of this vertex, right? And photon coming off of this vertex. So I have a electron, photon, or I have positron, electron, photon, and this is simple. And now it's what do I do with these? Well, look, those are 2 photons. Just connect them to your photons. Those are your outgoing photons. Now I figured out a way to get incoming and outgoing with only 2 vertices. So this was way better, or at least by better, easier to draw, and it's going to contribute far more to the odds of this event actually occurring, to figuring out the exact calculation. So I had 1, 2 vertices. That's going to be more important. This is going to be the leading term. That's why in this little quantum field theory calculation I did, let me see if I can get to it. Oh, no, get out of here. So I was just calculating this one. This was the most important one because it only had 2 vertices. Let me see if I can find, I never put in the numbers, but so you don't get to see the 1 over 137, but it's just implied by the constants in here. So when we drew that one, it would have 2 vertices. It's more important. So that was the easiest one to draw. I'd like you, so your homework, find a third possibility. So I drew 2 of them. There are literally an infinite amount. Think of some way to connect these incoming and outgoing states to each other that aren't either of the ones I just drew. And I'll give you some more practice because we'll do this next one as well. And then your homework's going to be to draw a possible way to connect this one and this next one. Just figure out one way to do it that's not what I already showed you. So let me show you how to connect these. And so to give you some idea, time's running to the right, space is up and down. So like if I was an observer, let me just make it clear. If I'm an observer, I'm sitting here and I'm like, whoa, look guys, there's an electron and positron heading toward each other. Again, from the electron's point of view, it's like, no, I was an electron and now I started running back in time. And at any given moment over here, you see two things because I went back in time and recrossed that timeline. And then I'd get over to here and I'd be like, whoa, they annihilated. And then I'm way over here and I'm like, oh, shoot, now there's two photons. So, you run this in your particle collider. You've got a big detector, and what comes out is there's two photons out. What happens in here? I mean, we aren't in there. We aren't inside the detector. The detector's sending us what it found coming out. So, what actually occurred in there before these particles streamed out through the detector is hard to say. All we get is the outgoing state. So what would this one represent, this process here? Let's see, you've got an electron coming in and a photon coming in. So sort of the simplest way to do this, and then outgoing is, again, electron and photon. Now, you're not allowed to do this. Some kids are like, oh, man, I got you. Boop, electron. And then they're like, boop, photon, did it. It's like, yeah, true. This is true. This is definitely a possibility of how you could start with an electron and a photon and end with an electron and a photon, but they never interacted. Like, they missed. So you made a pretty crappy collider here. You made a collider where the electron never actually collided with the photon, and yes, that's possible. But it is not interesting. We're not asking what happens if an electron in Louisiana remains in Louisiana and a photon in Las Vegas remains in Las Vegas. It's like, yeah, that's possible. But that's not what we're talking about. We're asking, how could you run an electron into a photon and then get an electron and photon out after they collide? So one way to do it, let's see, you could run this electron here. It can just hit the photon. And so if we have photon coming in here, the only other option for this vertex, remember I need like electron, photon, and then another electron. So I'm going to draw electron here, and I got to keep that arrow running. Arrow's got to keep running this way. And then over here, well, I need another vertex, so I'm going to run my electron this way. That's fine. Notice my arrow continues on. It never like runs into another arrow in terms of like this. When I say run into, I mean like that. That can't happen. And then I've got my photon coming out here. So this is not too bad. Not too complicated. It's got two vertices. That means it contributes a lot to calculating the probability of, this is called electron scattering. So an electron absorbed a photon and then it got knocked out, and another photon. So you scattered a photon off an electron is what it would look like. To someone watching, they'd be like, wow, that photon bounced off that electron and then knocked it in a different direction. So this would be the most important term. So this is one possibility. I'll show you another one, and then again, I want you to figure out a different way to do this top one and this bottom one here. So that was one possibility. Look, I'll show you a harebrained. I'm just going to give you the worst. Let's just do the most ridiculous here. Let's just make this horrible. So what's another option? Let's say, okay, we'll start off the same way. I'm just going to run this straight into the photon. I don't think I have much choice there. There we go. And then I'm going to have a electron come out because that's the only option that I'm allowed to have. And then let's say, let's have an electron come down this way. Why not? And a photon pop out here. These are virtual particles, remember. Okay, so that's allowed because I have electron, electron, photon. And now I'm going to, okay, here we go. I'm gonna, this is gonna be a nightmare. I'm gonna make a electron, positron. Here we go, the arrow's gotta continue. And then I'm gonna bring this right back. Oh God, this is bad. Bring this right back down. Oh man, that's bad. Okay, hopefully I can get to the end here. So this could zoink, over to here. This is going to be ugly, sorry. So that photon, let's say, is the one that actually gets out of the detector. I still need a photon here because that's a vertex. So electron, positron, and all of that business. When I draw an arrow straight down, you might be like, wait, is that a positron or an electron? Because it's not really moving through time. Again, these are just sort of graphical ways. It could be either, depending on whether it's slanted a little in this direction or whether it's slanted a little that way. I'm not going to worry too much whether you draw it straight up and down. It could be kind of either, depending on how you draw that triangle. Okay, so now I need to bring this photon over here. Yeah, look at I could do this. I'm going to bring this electron. Let's say it comes over here. It's not going to run into this. I'm going to draw it over. Right, so this is not to be interpreted as what's actually happening in space. It's just sort of a way to figure out how these all combine. So I should have drawn this, in 3D, and this photon came over to here and interacted with this one. I just need a way to connect these two. This photon comes over to here, and look at what happens. Boom. This works out. I've got electron, boink, hits a photon, comes out this way. So this is a terrible example. Like, I wouldn't recommend trying to draw anything this complicated because, for one, it's hard to draw. It's hard to keep track of. You start crossing over lines. And for two, let me count up the vertices here. You've got 1, 2, 3, 4, 5, 6. Yeah, it's not going to really matter that much. It might. Like, if you're really going to be careful with the LHC, you might need to start going to this many. This would be about as complicated as you probably want to calculate. Anything past this, it's going to be more precise than we could even measure. These are the ones you hand to the grad students. You're like, hey, grad student, I don't want to do this as a professor. You crank away at this for a freaking, 6 months and see if you can figure it out. This one probably wouldn't take 6 months, but it's going to be a little bit nasty. And so that's another option. I showed you 2 for each of these. You have to draw a third option. Again, there's infinitely many. Don't make them this hard. You don't have to make them that hard. Figure out an easy way to connect these. I think I stole the 2 easiest ways, but there's slightly harder ways. Your homework is to figure out how you could find another way to connect these incoming states to these outgoing states using only the vertex rule, which is electron, electron, or electron, positron, photon. So figure out a way to do it here, figure out a way to do it there, and then we'll make another video. I'll show you how to do more of these. Don't worry about going on further in this packet. Just figure out one way to do these, and then, oh yeah, you got to share it with me somehow. Submit your image. I'm going to make in Veracross. I'll make it so you can like submit document. Submit within Veracross. You can just submit your within that little assignment. You can hit a submit button and you upload. Just upload a picture. Just take a picture. Draw this on paper of one way to do this, one way to do this. Draw it on paper. Take a picture with your phone. Upload it into Veracross into the assignment. So I'm going to make an assignment that says, QED homework 1 or whatever. So look for that. Try that out. Let me know if you have trouble later in the week. Maybe next week. We'll try this for a while. Maybe next week we'll meet up real time and do some real time help. Maybe we do it later this week. We'll see how these goes. If this is a complete crap show, maybe we'll meet up and we can do some real time stuff. All right. Good luck.